Okay, so good evening, ladies and gentlemen. And today I will present you a speech towards design of quantum electrostatic classical and quantum logical gates. And my name is Piotr Imiński. Firstly, I will talk a bit about the quantum technology landscape and possible applications, and then I will talk about the beginning of our research. So quantum computing has been a major area of research for the past 3 decades, with companies like IBM and Google leading the way using superconducting qubits. However, one area gaining momentum is semiconductor quantum dots, which are showing significant potential due to their scalability. What makes semiconductor quantum dots so attractive is their compatibility with existing CMOS technology, which is widely used in classical computing. With advances in lithography, we can now create quantum devices on a nanometer scale, opening up to possibilities for large-scale integration of quantum systems. And what's more, unlike superconducting qubits, semiconductor devices are more easily scalable, which is easier for further quantum networks and quantum computers. And although semiconductor quantum dots offer great promises, and they come with their own set of challenges. And one of the biggest obstacles is maintaining coherence in quantum system. And coherence refers to the ability of a quantum system to remain in superposition state without interference from the environment. And in semiconductor system, charge noise, so the random fluctuations in the electric field, affects coherence, causing errors in quantum computations. And if we can solve the coherence problem with maintaining the scalability of the semiconductor devices, we will be able to integrate them into quantum computers that can outperform the classical components. And now let's talk about the basic concept of semiconductor quantum devices. At the heart of these devices are transistors, which function as quantum wells. So tiny regions that can trap individual electrons. And these trapped electrons represent quantum information, also known as qubits. And by applying voltage to these quantum wells, we can control the position and movement of electrons, allowing us to manipulate the quantum state of the system. A simple system would consist of two quantum wells. An electron trapped in one well represents one quantum state, and when it tunnels to the other well, it represents a different state. And this is the basis for a qubit, which can exist in superposition of both states simultaneously. Okay, and now when we take multiple quantum dots and place them next to each other, something interesting happens. The electrons in these quantum dots interact with each other via electrostatic forces, especially Coulomb interactions. And this interaction leads to quantum entanglement, a phenomenon where the state of one electron is linked to the state of another, regardless of the distance between them. And in quantum computing, entanglement is key because it allows qubits to process and share information in ways that classical systems cannot. And in the case of semiconductor quantum dots, we can create entanglement by placing parallel transistors, allowing the electron in each to influence each other through these electrostatic forces. And this entanglement between qubits forms the foundation to quantum computations. Now let's dive deeper into quantum entanglement and within semiconductor devices. Imagine two transistors, one on the left and one on the right. The electron in the left transistor can tunnel into the right one, and vice versa. Through this tunneling process and their electrostatic interactions, the qubits become entangled. And this means that measuring the state of the first qubit will immediately tell us the state of the second qubit, even though they are physically separated. And entanglement is a unique quantum phenomenon with no classical equivalent, and it allows quantum computers to solve complex problems much faster than the classical ones. But electrostatic coupling allows for more controlled qubit interactions compared to magnetic field-based systems like superconducting qubits. What's particularly interesting about this approach is that it can be implemented using CMOS technology, which makes semiconductor qubits highly scalable and easier to integrate into existing computer systems. And one of the most promising applications of semiconductor quantum dots is the development of quantum neural networks. In a quantum neural network, we arrange quantum dots in chains where electrons can propagate from one quantum dot to the next, much like how signals travel in classical neural networks. But the difference is that because of the quantum properties of these systems, electrons can be in multiple states at once, allowing for parallel processing on a scale far beyond what classical computers can achieve. And the position of electrons in these chains can be controlled by external voltage applied to gates placed above the quantum dots. And this allows us to dynamically control the connectivity between quantum dots, creating programmable quantum circuits that can solve very complex problems. The next critical concept is quantum transport. So it is the way that electrons moves between quantum dots and how it relates to coherence. In semiconductor quantum systems, the movement of electrons is modeled using a tight binding model, which helps us calculate the probability of an electron tunneling between quantum dots and how its quantum state changes over time. However, maintaining coherence during these transports is crucial. And as I mentioned, charge noise and other environmental factors can cause the system to lose coherence, leading to computational errors. In this case, to solve this, we need to carefully design the quantum dots and control the external voltage to ensure stable and coherent qubit interactions. And another exciting development in the field of quantum computing is creation of hybrid quantum systems. And such a system combines semiconductor quantum dots with superconducting qubits. What's the most interesting is that it takes the advantage of the strength of both technologies. In a hybrid system, semiconductor quantum dots can be coupled with superconducting qubits via the electrostatic or inductive coupling. And by linking these two systems, we can enhance the coherence time and increase the computational power of the quantum systems. One example of this hybrid approach is using a Josephson junction, which are superconducting devices that can interact with semiconductor quantum dots. And this hybrid system allows for high-speed qubit interactions and opens new possibilities for quantum computations. Now, in terms of architecture, one promising approach is using topological qubits. And topological qubits are known for their robustness against noise and errors, which makes them highly reliable for quantum computing. And recent research shows that hybrid system combining semiconductor quantum dots and superconductors can exhibit topological phase transitions. And this means that the system can shift between different quantum states in ways that protect the qubit from external disturbances, making it more resistant to the decoherence. And these error-resistant qubits are ideal for building large-scale quantum systems, where the stability and accuracy of qubits are essential for performing complex calculations over long periods of time. Now we can move on and talk a little about practical application of semiconductor qubits. And one of the most attractive aspects of semiconductor quantum dots is their potential for scalability. And as CMOS technology continues to advance, we can now manufacture qubits on the same chips used for classical computing. And this could enable mass production of quantum devices and bringing quantum computing out of the lab and into the practical uses. And in terms of applications, semiconductor qubits could be used in a wide range of fields, including quantum simulations, AI development, and drug discovery, and also cryptography. And these fields require computational power far beyond that classical computers can provide, which makes computing the next frontier in solving real-world problems. And now let's talk a bit about the basics of logic gates. And so we have the OR gate, which providing the input gives us the logical output 1 in the case when we provide to one or both channels the input. We have the XOR gate, which provides us with logical output 1 in case when we provide an input only to one or the other channels, not the both in the same time. We have also an AND gate, and in this case we have logical output of 1 only when we provide input to the both gates at the same time. And for example, NAND gate, it's basically the negation of the logical gate AND. So in our approach for the two-body system with electrostatic interaction bias externally to electrostatic gates and functionalize for logical gates implementation. And in this case, we use the Hamiltonian formalism, which is a powerful framework in classical mechanics that focuses on the total energy of the system to describe its evolution over time. It was developed in the 19th century by William Rowan Hamilton, building on the earlier work of Joseph Louis Lagrange. And in the Hamiltonian approach, the system is described by generalized conditions, coordinates, and the corresponding conjugate moments. The Hamiltonian function, which we describe here, as can be seen, typically represents the total energy of the system, which is the sum of kinetic energy and the potential energy. And the key feature of Hamiltonian formalism is that it replaces the second-order differential equations in Newtonian mechanics with a set of first-order differential equations known as Hamiltonian equations. And we can be can you see and these equations describe how the position and momentum of the system evolve over time. And one of the main advantages of the Hamiltonian approach is its ability to handle constrained systems and complex motions more easily than traditional Newtonian methods. Then, in order to simulate our gates, we simulate potential using, in this case, exponential functions. And here we can also see the electrostatic potential distribution in two dimensions and how it was looks. And then we conduct our simulation. Firstly, for 1 electrons fired in separate tunnels. And as you can see here, it gives us the logical output 1, because it will be read on the output. And also we can see that we can see that the energy is conserved in this condition. Next, we performed a simulation when 2 electrons were fired simultaneously. And also here we can see that they will give our logical output of 1. And also the energy is conserved here. And then we move on to describe the noise, adding it to the simulation in order to get more real-world situation. And after that, we performed 1,000 tries. And here we can see the probability maps of the output. And as you can see here, it also gives us the logical output 1, which will be good for our page. Also here, we can see the probability maps for the situation when we provide 2 electrons simultaneously in the square channels. And also in this case, we will obtain the logical output 1. Next, we move on to simulating the XOR gate. And also we use exponential function, but here we change it a little bit in order to represent this gate. And here we can see the outputs of our simulation of the electrons separately in these channels. And as you can also see here, they will be read as logical 1. And also the energy is conserved in this situation. However, when we put 2 electrons in the same time, in this case, they result in logical output 0, because they won't be read. And also in this case, we added some noise in order to better represent the situation. And here we can see the probability maps of the output. As you can see, it's for the electrons fired separately, and they will be read on the output, which results in logical output 1. And then we, in our plans for future, is we move on to simulating more real-world potential, and then conduct the simulations. And we also be simulating different potentials, and then we plan to quantize our solutions in order to provide the quantized version of logical gates, and then we will expand it on the multiple channels, and in order to at the end try to simulate the quantum neural networks. And at the end, hopefully, we will try to verify the models experimentally and check its correctness. Thank you, Francis, and thank you very much for your attention.
Thank you very much. Do you have any questions or comments?
What type of noise have you implemented in the simulations? Was it Gaussian noise, Poissonian noise, uniform probability noise?
Yes, so I was trying to implement the Gaussian noise in order to simulate the real world situation. However, we will also try in future implementing different types of noises in order to get the more realistic results.
Thank you. Any questions? Maybe I will ask, in case of your presentation, you have, for example, OR gate and XOR gate with three-dimensional potential. Could you describe this area? So it is the OR and XOR which are implemented in the using quantum dots, or which object is analyzed?
Yes. Firstly, we try to implement it classically in order to get the feeling for it. And then in the final result, we try to represent we try to represent it as the quantum dots connected. Hopefully, at the end, we try to implement quantum neural networks.
And it is the position of the two electrons
Yes.
in this area.
Yes, yes.
So very useful will be the picture with the our implementation before.
Oh, yes.
Thank you very much.
Yes. Thank you.
Okay. So the next presentation, quaternion consideration on analysis view on couple single electron lines by Wojciech Nowakowski.